Hi class. I'd like to finish our discussion of the asymptotic evaluation of integrals by considering the method of steepest descent. Last time we discussed the method of stationary phase, which had to do with using the critical points of oscillatory integrals to determine the leading asymptotic behavior. And we pointed out that it's actually rather difficult to improve on the leading approximation, and we needed a more powerful method if we wanted to understand what was going on in greater detail. The method of steepest descent, which we discuss here, is that more powerful method. So the kind of integral that we're going to be talking about is a Laplace integral, but we've written the Laplace integral as an integral in the complex plane around some arbitrary contour C of a function which is a function which has a prefactor g, which is a complex function of z, and an exponential e to the x f of z, where f is a function of z. X is a real variable, and we're interested in extracting the asymptotic form of this integral, this function of a real variable x, as x goes to plus infinity. The basic idea generalizes what we've been talking about with Laplace's method and the method of stationary phase. We expect that the behavior of the integral is going to be dominated by the stationary points of this function f of z. Now we're interested in the stationary points of the function in the complex plane. So we're looking for points where f prime of z is equal to 0. So let's call the zeros the critical points, say a point z0. Now, what we're going to do is we're going to use the freedom to adjust the contour. Remember, what we learned in the complex analysis portion of the course is that as long as we don't cross any singularities, we're free to move the contour that defines the contour integration that we're interested in however we would like. So we're going to modify the contour C to go over the stationary point in such a way that we can isolate the leading behavior and compute the contributions from one or more critical points of the integral. So let's set this up. The function f of z will have a real and imaginary part, which we've traditionally called u and v. If we look at the magnitude of the exponential, the magnitude e to the x f of z, the imaginary part just gives an oscillating contribution, oscillating phase. So the critical, the magnitude of the exponential part is e to the x u of x and y. So the size of the contribution is determined by the value of u at any potential critical point. So if we have a critical point z naught, which is x naught plus I y naught, so it's a critical point, we know the derivative of f with respect to z, the complex derivative, is equal to 0, both the real and the imaginary parts. If we apply the Cauchy-Riemann relations, what that means is that the partial derivative of u with respect to x and its derivative with respect to y both vanish at that point. So the critical point really is a maximum or a minimum of u. In fact, we know more. It's actually a saddle point. Why do we know that? We know that u is the real part of a complex function, an analytic function. Therefore, it's harmonic. So the second derivative of u, rather the Laplacian of u, is equal to 0. So suppose that we're going over the saddle point, we're going over a critical point in the x direction. Well, because of Laplace's equation, if the second derivative with respect to x is positive, the second derivative with respect to y is negative. So in any direction we go, if one direction is concave downward, the other direction is going to be concave upward. So what we find is that for this general kind of a Laplace integral, whenever we look for examine the behavior of the critical points in the complex plane, those critical points are actually going to be saddle points, as illustrated by this diagram here. So in general, z naught is going to be some saddle point, and now we can see, here we've plotted the magnitude of u, we can see what we want to do in order to adjust the contour is we want to go over the saddle in such a way that we cross the saddle over through a path of steepest ascent and descent and go through the saddle point without going through the pieces where the saddle is instead going upward. So there are ridges over on this side, and there's a saddle with a decreasing value of magnitude of the function on this side. We want to adjust our contour to go over the saddle in this direction. So we're going to have to figure out where the critical points are and how we're going to readjust the contours in order to evaluate the integral. So How does that work? If we expand the function f of z near a critical point, f of z, if we just expand in the Taylor series, it has the value at z naught plus the derivative vanishes because z naught is a critical point, plus the second derivative. In general, the second derivative at z naught is a complex number, which I'll write as rho e to the I theta. If I'm interested in a path around z naught, let me take a straight line path at some orientation, some fixed angle phi, and we'll let s parameterize how far we are from z naught. If I then examine the behavior of f of z near this critical point in terms of these variables, I see it's f of z naught plus 1/2. This is the value of the second derivative. This is z minus z naught squared. If I look at the real and the imaginary parts of this, I see that I get a possible Gaussian integral. This is just a constant. I get a possible Gaussian integral in s, but it depends on the relative phase of the second derivative and the direction of the path that I'm going to deform my contour around. In particular, if I want this to look like a decaying Gaussian, whose value I can evaluate, I want to choose my angle phi, which is the direction that I'm going in the complex plane, so that cosine theta plus 2 phi is equal to -1. That maximizes this negative part, but it also, because cosine squared plus sine squared is equal to 1, it also sets the sine equal to 0. So when we go over the steepest descent path, here I've plotted the real value of the function. The real value of the function is going to vary rapidly, but in fact the imaginary value of the function is constant. So this generalizes what we did with the method of stationary phase. So if we want cosine theta plus 2 phi to equal -1, we need theta plus 2 phi equal to plus or minus pi. So we need to determine the direction we go over the contour in terms of the phase, the argument of the second derivative, plus or minus pi over 2. And this is the complicated part of the method of steepest descent. We now need to figure out, given the contour we start with, how do we deform the contour to go over the critical points, to go over the saddle in the correct direction, while not crossing any singularities and still having a convergent integral which defines the integral that we're interested in. We'll talk about this in a particular case, the case of the area function, in the next video.